Now, as I said, a system of particles is moving. How do you calculate the total momentum of the system of particles? Now, when we apply, obviously the idea of momentum comes again from Newton's second law and third law, and the momentum of the system of particles will be equal to the mass of the system of particles into the velocity of center of mass. That's it. The total, if you want to know when a system of particles is moving, I'm throwing, this is moving in whatever way it's moving, the momentum of the system of particles is equal to the mass, the total mass of the body into the velocity of the center of mass. That's it. Okay. We already saw this proof earlier, but I'm going to just show it you again. If we consider the position vector, okay, of the center of mass is equal to m2r2 plus the position vector, sum of mass into position vectors of all the other particles making up the system. It's just divided by m1 plus m2 plus mn, which is capital M, and I'm going to take the mass of the whole system here. Okay, I differentiate it once, I get mass differential of position vector, I get the velocity vector is equal to m1 v1 plus m2 v2 plus mn vn. So if you look at the system of particles, this right hand side is equal to the momentum of each of the particles. It's a sum of each of the momentums, linear momentum. Okay, I'm dealing with linear momentum. It's equal to the linear momentum of each of the particles in the system, which is definitely equal to the total momentum of the body. So the total momentum of the body is equal to mvc. And you've seen that, and that's exactly what this is about. So this is a proof which shows that such a complex body, moving body, however complex it is, to find out the momentum of the body, all you need to find out is the total mass of the body into the velocity of the center of mass. So this is how you can see center of mass allows you to analyze the motion of a system of particles so elegantly, so simply. It allows you to measure it. In fact, many times we talk about, applying from this, we can apply, all Newton's equations. We therefore have dP by dt is equal to F external, isn't it? So when the external force is zero, the total moment, the momentum of the system of particles is conserved. The important thing here being that, see, the internal forces can go on, but internal forces cancel out. Therefore, a change of momentum happens only when there is an external force. Okay. So just to give you an idea about when, where the applications of center of mass happens, in a real life, you have, let's say, a long jumper, right? So when a long jumper takes off, right, when he jumps, the center of mass, let's say, he shoots forward. Remember that his center of mass is going to follow the path of a parabola, right? And what the long jumper can do is that he can change the shape of his legs or raise his legs in such a way such that he touches the ground at the latest moment. Okay, so whatever you see him or moving his legs and hands, in the air to gain maximum distance, remember that the center of mass is just going to follow a parabolic path. Okay, and using because any other force that comes is an internal force, right? Similarly, I think this can also be explained, behind a ballerina who makes a jump and almost appears to be floating in the air. Once you make the jump forward, your center of mass is going to move like a parabola, just like a particle which is given an initial velocity and it moves as a parabola. But how you make the graceful is with the movement of the legs and the hands, you can make that movement very graceful, or you can change it, the way you want. But don't forget that the center of mass obeys all our laws of motion, and it is going to move like a parabola. Okay, thank you.